In this work, we present an evaluation benchmark for video inpainting, a task which enables the removal of objects, captions, and watermarks by replacing a given region with plausible content. Although video inpainting solutions have vastly improved in recent years, failure case analysis has still relied on isolated qualitative evidence. For example, large occlusion masks are known to hinder inpainting models, but can we quantify and compare this degradation at scale? And what other visual challenges in the video or mask will affect performance? To answer these questions, we designed the Devil benchmark, which provides a large methodically curated dataset for video inpainting, as well as a comprehensive evaluation scheme that measures inpainting quality under several different scenarios and metrics. The purpose of our benchmark is summarized here. We illuminate open challenges in video inpainting by focusing on large-scale content-oriented evaluation. Furthermore, our comprehensive evaluation scheme allows researchers to quantify and compare how their models respond to these challenges. To disentangle the effects of foreground and background content on the inpainting task, we collected background-only source videos and generated masks with varying motion and size. Furthermore, we labeled videos and masks according to the motion and size properties shown here, which our experiments show have a substantial impact on inpainting performance. To source our background-only videos, we searched Flickr for scenic landscapes which generally do not include foreground objects. We found a small number of users who upload high-quality content, and filtered their videos for foreground objects using mask RCNN and manual verification. From there, we split up our videos into 1200 3-second clips. After collecting our videos, we annotated them with labels that indicate how much camera and background scene motion is in the video so that we can control for them during evaluation. Camera motion refers to how much the camera pose changes over time, and background scene motion refers to how much the background scene itself is changing, independent of camera motion. For annotation details, please refer to our paper. Alongside source videos, we also produce occlusion masks controlling for foreground object size and motion. Specifically, we control the foreground displacement, which is how much the location of the mask changes over time relative to the field of view, the foreground pose motion, which is how much the mask shape changes over time, and finally the foreground size. To generate masks, we extend the procedural blob strategy of Chong et al. By adding greater control over these attributes. In our benchmark, we construct dataset slices, each characterized by one attribute, to see how that attribute affects inpainting performance in isolation. For example, for high camera motion, we would sample all occlusion masks, but only source videos that contain high camera motion. For high foreground displacement, we would sample all source videos, but only occlusion masks with high displacement. We randomly sample 150 video mask pairs per evaluation slice, and then evaluate a model on each slice to see how well the model handles the corresponding attributes. We adopt a comprehensive set of evaluation metrics that span 3 aspects of visual quality. Realism refers to how well the distribution of inpainted videos resembles that of real videos. Temporal consistency measures how much the colors of corresponding points in the scene change across time. And reconstruction measures how much the inpainted video resembles the ground truth at the pixel level. We ran 7 state-of-the-art models through our benchmark, making our study the largest head-to-head comparison of video inpainting methods to date. We found that method rankings change drastically depending on the metric and devil slice used, which highlights the importance of comprehensive head-to-head evaluation as is made possible through our benchmark. Using our content-based devil slices, we can compare and contrast how inpainting models respond to specific types of content. For example, we see from video samples that VINet and CPNet react differently to camera motion, and that this difference is reflected quantitatively in our analysis. Finally, our head-to-head comparison reveals performance trends among recent work. In particular, models that explicitly estimate optical flow tend to produce the best results, suggesting that flow prediction is key to good video inpainting performance. Furthermore, non-deep learning approaches perform well, suggesting that improvements can be made by modernizing older methods instead of just relying on deep learning advances. For more information, please visit our project page or reach out to us by email. Thanks for watching!